Hey, everybody. Welcome. Welcome to week 8, Intermediate Coding with SuperCollider, week 8. All right, today we're going to talk about the fast Fourier Transform, or FFT for short. And I just wanted to give a brief introduction before we dive in. So a disclaimer first, I am not an expert on the FFT. I have never had to do one manually, and like the real down and dirty detail level stuff of how it's implemented and how it works. I don't really know too much, but so do I get the gist of the FFT? Yes, I do. And I think I can do a pretty reasonable explanation, at least for students who primarily consider themselves musicians. So there may be a chance that something I say in this lecture is inaccurate or very possibly wrong, but we're just going to charge right in and see where we land. But I'm going to do my best. Hey, Seaborch. Okay, so along with the Fourier Transform comes the Fourier Theorem, which, to put it very simply, states that all periodic waveforms, or periodic signals, can be expressed as a sum of individual sinusoidal waveforms, each with very specific frequencies, amplitudes, and initial phases. That applies to any periodic waveform in existence, no matter how complex. So the Fourier transform is a mathematical operation that takes as its input some periodic signal or waveform or function, some pattern, some wave pattern that repeats. So basically, we call that the time domain, a function of amplitude as a function of time, and the output of the Fourier transform is data that corresponds to the spectrum of that signal, data that corresponds to information needed to reconstruct it as a sum of individual sine waves, so specifically amplitudes and initial phase data for all harmonic partials. There's also an operation called the inverse Fourier transform, or the IFT, which goes the other way. And you can go back and forth between these operations, and no data is lost. You take a signal, you apply a Fourier transform, and you get the spectral information. You apply the IFT, and you get exactly what you started with. And so the fast Fourier transform, the FFT, is a version of the generalized Fourier transform operation, which is meant to be applied to discrete signals, in other words, digital or sampled signals that consist of individual values in an order rather than something continuous. Right, the fast Fourier transform is meant to be applied to discrete signals, and it is a version in which a lot of redundant calculations are removed so that this operation can be performed in real time on a live signal with a sufficiently powerful computer. So you can speak into a microphone and be doing a Fourier analysis of that signal and messing with the data and doing an inverse Fourier transform and bringing it back into the time domain and playing it out of your speakers, all in real time. It's very exciting. So that's the introduction. In SuperCollider, there are two types of FFT. There's the language side FFT. So there's a method called FFT, which operates on instances of the signal class. And there is the FFT, all caps, which is, it's a UGen, ultimately. So it's something that deals with audio signals. And this is kind of how we get your average, your run-of-the-mill time domain signal, like a sine wave or a microphone signal, into what we call the frequency domain. So in this lecture, we're going to look at the language side FFT first, not as a means of making sound and making stuff sound cool, but as a means of unpacking and dissecting the FFT and kind of looking at it close up in slow motion. And then we will get into the proper sort of sound-related FFT and make some cool sounds. Okay, so the first thing we're going to do is very surgically, very artificially create a signal. And this is stuff we've seen before when we were talking about wave tables, which I think was week 3. So this is what I'm done here is I'm just picking a size. Oh, I forgot to mention the FFT. The the size of the signal that is analyzed by the FFT must be a power of 2. That is part of what makes it fast. When it's a power of 2, that's what allows redundant calculations to be omitted. So I've just mostly arbitrarily picked 2048 for the size here. And then I am just filling a signal with some sinusoidal partials. So it's going to be 2048 samples long. I've got amplitudes of 8 harmonics, the fundamental through the 8th harmonic, and then some phases of these. And so we'll just make that. And just to see what it looks like, we can plot it. And this is one cycle of a periodic wave that has full energy at the fundamental with no phase offset, nothing at the second harmonic, half amplitude at the third harmonic with a phase offset of 1/4 cycle, right? Pi over 2 radians, et cetera, et cetera, et cetera. You take these 1, 2, 3, 4, 5 sine waves, you add them up, and this is the shape you get. And this shape is going to repeat forever and ever at some frequency if we were to use OSC or some other UGen to play it. Maybe we wouldn't know the recipe, the spectral recipe, just by looking at this shape. I mean, certainly not. But the FFT is what allows us to go the other way. We start with this, and it reveals the recipe. All right. So what that looks like, language side, is we have to do a little bit of setup. We have to make another empty signal of the same size. We also have to prepare yet another signal, a third signal of the same size, which is filled with something called an FFT cosine table. It's a signal that is required for the FFT to do its magic. So the FFT involves complex numbers. So this is part of why I don't have a complete understanding of it. We think about complex numbers on the complex plane as having a real part and an imaginary part. And we can also think of those two-dimensional values as having a magnitude, basically the radius or distance from the center of the plane, and an angle, a rotational angle around the, some amount of radians around the unit circle. And it's the magnitude and phase, or magnitude and angle, that corresponds to the actual content. And there are lots of videos on YouTube of like people doing FFT animations where some periodic waveform is represented as a bunch of circles whose radii are joined end to end, and they're all kind of spinning at their own speeds, and so it basically draws the picture. Some really good videos. I'll put some links in the video description. But essentially, we're doing some complex math here. No pun, actually pun intended, I guess. And we're just going to do that. So what we have is something called complex, which is a complex number or a member of the complex class. And basically, this contains data that we're eventually going to use for representing the spectrum. And so what I'm going to do is plot two things. I'm using the magnitude and phase methods in the complex. These are instance methods for complex. Yeah, so there's magnitude and rho, which are synonyms, distance to the origin, and angle, phase, theta all do the same thing. This is the rotational angle. So I'm just saying, give me all the magnitudes, give me all the phases, and then I'm putting this plot in the upper right corner of my screen, and I'm going to plot in bar mode because I think that looks best. So this is the entire FFT. At first, it looks like, what the heck are we looking at here? And this is a size 2048, which means it's got 2048 what are called bins. And actually, we only really care about the first half because everything past the 1024 mark here is just above the Nyquist frequency. So it's just folded over data. And that's why we have a sort of symmetrical thing happening here on the top. But we're looking at all the magnitudes and all the phases here. And that's too much. So I'm going to instead just look at the first 15 or so. And this will be a little bit more pleasant to look at here. And right off the bat, we can see that the FFT has sure enough derived the spectral data. So this 0th bin here, I think corresponds to DC offset or 0 hertz presence. So we'll just ignore that one. In fact, we can just avoid plotting it altogether by just starting one bin earlier. So, and we can also, here's a nice trick with plotters. We can hold Alt and click, and we get the value of that, of where we clicked in the post window. So the vertical scale here is not quite right. We're going to fix that shortly, but just looking proportionally at the bars on the upper graph, we have 1, 0, half, 0, half, quarter, and then 1/10, which is exactly what we have here. So these are our amplitudes. They're scaled in a way, it says 500 here, so it's scaled somehow related to the FFT size. And then we can look at the radians here, the phase data. So this one here is, let's get rid of some of these windows. Let's get rid of that one. Yeah, so phase data here is negative pi over 2, which is not what we have. And the phase data for the third harmonic is, well, it's basically 0. It's negative 8 times 10 to the negative 9, so it's basically 0. That's also not right. The reason the phases are not correct is because we're filling a signal with sine waves, but the FFT needs a table of cosines. So we actually need to add pi over 2, because sine and cosine are a quarter cycle out of phase from each other. And then I'm also going to wrap this value so that it's within 2 pi. Because if some value is already close to 2 pi and we add 2 pi, it's going to exceed 2 pi. And I just want to visualize these so that everything is between 0 and 2 pi. I think it makes it a little bit more readable. And then what I'm going to do here is just, I'm not exactly sure what the correct math is to make the magnitudes consistent with what we initially put in. What you can do is just what I've been doing is normalizing them and then scaling by the peak value in the signal, which is 1. That's the highest value in the signal. Normalize scales them to 1 just in case the highest value is not 1. This puts them at the, so this is, I don't know if this is like mathematically robust, but it does make everything look correct. So now the vertical scale on the magnitudes plot is 0 to 1. So we have full amplitude, half amplitude for the third and fifth harmonics. That's consistent, right? 0.25 and then 0.1. And now the phases are correct too. So the phase here is, well, it's 2 pi, which is the same as 0. This one is pi over 2. That's consistent. This one here is pi. So it's, now we've got it. We've got the data. There it is. Right? So here's a plot of our FFT. I don't actually know where these phase values come from, like the ones that are associated with 0 amplitude. It's just a quirk of the FFT, but because the magnitude is 0, it's the point in the center of the complex plane rotated around by, so it's not even really rotating. All right. So that's a simple example. We just have a very simple spectrum. Let's do it with an actual sound file. So boot the server. And I am going to pull in that same file of me talking about delays that we have been working with in the past 1 or 2 videos. So that sounds like this, but that's okay. We can make it sound different by adding an effect. Right? We can make it sound different by adding an effect. And here's the sound file. It's actually quite long, and I'm not even sure why I did this. That's not meaningful at all. Okay. So first question, and here it is in Audacity as well. But that's okay. We can make it. Question 1 is, hold on, I thought the FFT only operated on periodic signals. This is not a periodic signal. It's just me talking, right? It doesn't repeat. It doesn't have a frequency. So how in the world does the FFT work on a signal like this? And the answer is, it takes little chunks at a time, what are called short time segments. So for example, like the FFT size was 2048. So 2048 samples divided by our sampling rate is about 0.0426 seconds. So the first thing it's going to do is grab this chunk of data, right? And then it'll jump over by some amount and take the next set of 2048. It usually doesn't go contiguous blocks. There's usually a little bit of overlap. So it just goes through and takes chunk, chunk, chunk. And I'm going to manually take my own chunk, which is, I think I've prepared this ahead of time. I'm going to free this buffer. And I'm going to, there's some additional arguments when you do buffer.read. You can say start frame, which I'm going to start 0.32 seconds into the file, and I'm going to read exactly 2048 samples. And that sounds like this. Right, real short. We can plot it. It's a little just chunk of audio. And let's go and find this in Audacity. So it's 0.32, and it's approximately 0.42 seconds. So it's like this chunk. And go away, go away. You can see, right? That is it, I think. Can try to line it up ever so perfectly. Sure is, right? There's our little chunk. And so what, oh, I lost it. What the FFT does is it says, okay, I'm supposed to do an FFT of this chunk. I will just go ahead and pretend that it is one cycle of a periodic wave. It just pretends that this is the actual waveform that it's dealing with. It just sees this little slice and it says, okay, I guess this is one cycle. So in the FFT's brain, it sounds like this. And so it's going to do an analysis and give us the spectrum of exactly how much of the fundamental is present, the second harmonic, the third, the fourth, etc., all the way up to the Nyquist frequency. How much frequency, whose period is this long, half the sampling rate. And we're going to get that exact spectral recipe. So let's do it. All right, so there's that. And so the first thing we have to do is read these buffer samples into a signal object. And that's a little bit more complicated than we might like, because buffers are server-side objects and signals are language-side objects. So what we're going to do is use this getN message. This is an instance method for buffers that results in an OSC message being sent from the language to the server saying, I would like a certain number of sample values from this buffer. Please send them to me. Please and thank you. And so we say start at 0, give me this many samples. So in this case, this means all of them. And then there is the third thing is a function, which is evaluated once the data being sent from the server to the language is complete. And we can pass in that array of values. So frames, we declare an argument to represent the array of sample values that we requested. So this frames is going to be an array of 2048 values, and it's just the individual sample values in that segment. And so then we say sig, which is a new empty signal. We're going to use wavefill, which takes yet another function. And this, I would say, read the help file for the wavefill method in the signal help file. We get to pass in 3 arguments. One is the value along some interval. This is the value that's already in the signal, which that's all going to be zeros because it's new and empty. And then an index, which is the only thing I care about. So basically, I'm just going to say fill the signal with each item in the array of buffer sample values that arrived. So it's a little complex looking, but it does, once you get your brain around that, then we have sig.plot. There we go. Sig is in fact a signal, and there it is, right? So they look exactly the same. This one is a buffer plot, this one is a signal plot, same data. It's just one of them is on the server, one of them is in the language. Okay, so now that we have it in a signal, we can do our FFT. So I'm going to copy and paste some more stuff here. All right, window.close all if we want. So we've seen all this stuff already. Right? We create our imaginary part of the complex numbers. We prep a cosine table. We perform the FFT. And then here I'm just doing 2 extra steps. So just normalizing and scaling the magnitudes based on the peak value in the signal, and also offsetting our phase values so that they represent the phase of sine waves instead of cosine waves. So shebang, that's finished. All right, so we've done all the FFT math language side, and here I've got some more code here. So I just have a variable, which is the number of bins we'd like to view. We're going to set it to 50 initially. Keep in mind there are 2048 bins, the first half of which are the usable ones. The other half is a mirror image. Well, at least the magnitudes are mirror imaged. And so I am just plotting the magnitudes and phases. Don't even know if I need... Oh, yeah, I decided to put minimum values in here. So this is the minimum value for the magnitudes, and this is the maximum value for the magnitudes. It's just the peak of the signal. Minimum value on the plot for the phases is 0. Max value is 2 pi. So just making it look nice, basically. So here we go. It's first 50 bins of our FFT, of our... it's like me, it's part of the word me saying that in, but that's okay. So here's the spectrum of that sound. And let's actually let's just do some just regular brain thinking here. So just look at this, we're pretending this is one cycle of a periodic wave, and we can see that it's got periodic behavior that happens within one cycle. Because look at this little, we got this shape here, and I didn't mean to take a picture of that. We got this shape here. This screenshot is so laggy when okay, well, yeah, this shape here, this shape here, this shape here, this shape here, and this shape here. This is not the same, right? It's obviously changing, but there is some sort of inherently fundamental or inherently periodic behavior that happens approximately 5 times in one cycle of this imaginary periodic wave. We can also see that there's kind of an up, down, up, down, up, down, up, down, up, down. Right? So there's definitely some stuff happening at, this larger one, 1, 2, 3, 4, 5, means we should see some energy at the 5th harmonic. This faster one means we're probably going to see something at the 24th, 25th, 26th harmonic. And then there's also wiggles happening here. This is probably I don't know, 70-something harmonic. And we even have really little wiggles happening here. So there's all sorts of sine waves going on here. We could even look at the entire thing real quick. Just for fun. So here's the entire spectrum. So we have, this first peak is probably 5. I think this is 10. Here's our 24, 25, 26. We have yet another peak up here, and then a little bit of data and tiny bits of data sprinkled all the way up. So it's a pretty complex spectrum, right? It takes a lot of sine waves to make this very unique shape. Let's go back to our 50 version. So here's I believe this is the 5th harmonic, right? We're looking at the DC bin. Don't want to look at that. Okay, so, well, actually, I liked it better the other way because the numbers line up. So here is our, 5th harmonic, amplitude at approximately 0.15, 10th. Right here, so we have a local peak centered on the 26th harmonic. All right, so that's all working. And now what I want to do here is do a little Frankenstein thing and build it back up from its component parts. Right? It's it's alive. All right. So I got some more code that I'm just copying and pasting to save some time. And it is this stuff here. All right, and I'm not going to spend too much time on this because it's something that I think is good to pause and study and copy and mess with it on your own. But basically, I have I'm going to be plotting some number of harmonics, and this is how many harmonics I want to plot, individual harmonics. So I'm filling an array of that size with signals, and I'm just doing some math here to basically isolate each individual harmonic as I fill the array. So this is an array that is 1 followed by it's an array of this size that starts with a 1 and then has zeros for the rest of it, and I'm rotating that array for each harmonic. And rotating an array looks like this. So if we don't rotate it, it's the same. Rotate it by 1, everything shifts over. The last item gets put in the first slot. So it's just imagining the array as being the ends being connected and then just kind of rotating it around. So that's how I'm isolating each individual amplitude. And so I'm using signal.signFill to fill a bunch of individual signals with each harmonic. And then I'm grouping them by 8 so that when you clump, so here's the array 0 to 29. When we clump, it makes like sub-arrays of that size. So it subgroups them, basically. And I'm doing that because I want to plot 8 in a large, thin vertical window, and then the next 8, and then the next 8. So I'm treating these harmonics just arbitrarily in groups of 8 because I think it looks nice on the screen. And then we're going to iterate over these clumps and plot each one and position it appropriately on the screen. And then I also flatten the array of harmonics, which undoes the clumping. And we're looking at all of them, and we're going to add them together. All of the harmonics that we've chosen to deal with, and then we plot that as well. So let's just close all, get this back, and then we're going to do just 8 harmonics. Okay? So here is our FFT, our spectrum, and here are the amplitudes, the sine waves from the amplitudes and phases of the first 8 FFT bins. So fundamental, second, third, fourth, fifth, sixth, seventh, eighth harmonics. And as we see over here, the fifth should be and is the highest one. So and then we add these all together and we get this. In fact, I should probably scale this plot. -1, max val, +1. Let's close this. Let's close that and do it again. So this is the sum. And because this is has the greatest amplitude, that's the one that has the most influence on the shape. Right? So let's do 16. No, let's do 32. 32 harmonics. There they are. How cool is this, right? So here's our FFT, and there's our fifth. Then we had a little bit of energy around the 10th and 11th. Right, so we had a little bit of activity going on there, and then not too much happening until we get to the 25th, 26th, 27th. That's a considerable amount of energy. It's higher. It's actually the greatest amplitude, I think. And so we sum them together, and it looks like this. Now, let's go find our original one. This is what we're building towards. This is the pre-FFT buffer data put into a signal. And you can see it's starting to take shape, right? It's working, right? We're getting it slowly but surely. Let's do this, and let's do 100. Takes a little time, and it crams a bunch of windows over here because it doesn't know where to put them. And so you can see, let's just get rid of these. We don't care about those. Sure enough, there is energy over, where is this one? We're not even looking at all the harmonics there. Let's look at that one too. So don't close all, give me 100. Yeah, so we have this little local area peak between 60 and 80. And that's what we're seeing kind of here, seeing some energy there. All right, and we add them all together, and this is what we get. It's not perfect, and also my amplitude scaling is wrong. It shouldn't be clipping past 1 like that, but all the same, you can see that we're getting closer and closer to what it is supposed to look like. Right, here's the original one, and here's the result of just the first 100 harmonics, not all 1024. But if we were to actually go and plot all 1024, add them all together, then these two windows would look, and I cannot stress this enough, identical. And they would be identical. The data in these two plots would be exactly the same. All right, so that's what's happening when we talk about the FFT in real time with audio. It's going through, it's taking a chunk of some power of 2 number of samples, doing the FFT, extracting amplitude and phase data, allowing us to mess with that data optionally, and then resynthesizing from the frequency domain to the time domain, sending it out on the audio path, and then it jumps to the next chunk, and it says, okay, here's my new periodic wave, and here's one cycle, and here it is again, and again, and again, and again, and again, and it all happens in real time. It's really incredible stuff. Very powerful in terms of audio processing. So, a lot of code to look at, a lot of stuff happening, but I think in the interest of time, we're going to move on to the FFT on the server. Okay. So we're going to clear all our buffers, start fresh, and probably didn't need to do that, but I'm going to load up that buffer again. Yeah. Thanks, Dimitri. But that's okay. We can make it. Okay, so we got our sound file again. This is the one we're going to primarily be working with. So if you want to read a couple of help files, which I do recommend, some of these have good information in them. There's the help file FFT, which just is an overview of this FFT unit generator. It talks about some, quirks and things, and describes the arguments. Some examples, various examples, good, helpful, simple examples. There is a help file called FFT overview, and I still have my search active. FFT overview. So this is a even broader look at the FFT library. Some information about how they communicate using buffers, how the data is written, and how to deal with multi-channel expansion. Probably not a good place to start, maybe. I think once you get some simple examples, you might want to check out FFT overview. And then there's also PV_chain UGen. This is not a UGen that we use explicitly or directly. It's the base class for other PV UGens, and the PV stands for phase vocoder. So all of these PV_whatever UGens are derived from this general class that we don't actually use. So like PV this, PV that, bunch of PVs. I think if we were to do an implementation search and type PV_, what if I hit enter here? Yeah, so here are all the various PVs. Some of these are extensions. If they're in SC3 plugins, I have some extensions installed. I don't really use them too often, but there's tons of PVs. All these are unit generators, essentially, that manipulate FFT data rather than time domain signals. All right, so in my first example, I'm going to make a brick wall filter, which is a pretty common thing to do with FFT stuff. Now, in the time domain, when we have time domain filters like LPF, HPF, low pass, high pass filters, standard stuff, EQ stuff, it's not possible to set a threshold and just slice down a vertical line and just remove everything below and keep everything above. Not possible in the time domain because of the time domain nature of signals, right? It's just not possible. It's just not how things work. But we can do it in the frequency domain. So I have a synth def here, and we're gonna break this down into individual steps. So synth def, name brick wall. I declare some variables. Sig, which is our live source signal. It's just play buff, looping through. It's going to loop through this buffer that we have. It's just one channel buffer, one channel play buff. And the first step, in FFT processing is to apply the FFT. Notice there's no AR here, right? FFT and the PV UGens are a little bit different. They don't really, I guess they don't technically run at the audio rate. They run at their own rate. Maybe it's demand rate. I'm not really sure. I'm not going to try to explain it because I don't really understand, but I do know that the method technically is .new, which we are allowed to omit, just like we do here, synthDef.new. And what we need to provide are two things, at minimum. First, a buffer in which the FFT data will be stored. And I think this overview talks about how FFT data is stored in the buffer. We don't really need to think about that, but it does need a buffer to keep that data in there. Basically, it's the stuff we were looking at here, right? It's the whole FFT. It dumps all of this data into a buffer, and yeah, that's how it works. Now, we can declare our own buffer, but all of the examples here use a class called local buff, which is basically a convenience that allocates a buffer in the synthDef that only this synthDef can use. And we provide the number of frames and the number of channels. Default number of channels is 1. And size is my FFT size. You can't modulate this value, much in the same way that you can't modulate the number of channels in a time domain UGen. You just can't do it. So you have to pick your FFT size. I've seen them go as high as like 16,384, and you can go lower too, but generally things start to not sound so great when you go below 256. So 1024 and 2048, these are kind of middle of the road FFT values that they're big enough, but they're also not too big, and so you don't really run into problems at either extreme. So I've just kind of arbitrarily picked 2048. This is something you can play with. Feel free to try 1024, 2048, well, you know, whatever you like. So we take an FFT of our signal using a buffer of some desired size. And then let's comment this out for a second. In this space here is when you can apply all of your FFT manipulation stuff. And at the end of it, you must apply the inverse FFT, which produces a time domain signal, and that is the thing we can play it out. Most of the examples use a variable called chain to refer to a chain of FFT processing, and so chain is not a time domain signal. It's spectral data. It's an FFT buffer. There's nothing special about the word chain. I'm just being consistent with the help files with a lot of the examples, just like there's nothing special about sig. And there's nothing wrong with then overwriting sig at the end of the FFT processing to be the new FFT process signal. So if I just run this synthDef and then make a synth, this will sound like it's going to sound completely normal, but that's okay. We can make it sound different by adding an effect, even though we are in fact going into the frequency domain and then coming back out, but we're not doing anything to the data in the meantime. So what's happening in real time, very, very fast, is the server is saying, all right, let's take an FFT of the first 2048 samples. Boom, there it is. We have the data. The user does not want to do anything to it, so we'll just, you know, put it back together, and we have our original chunk, and then it goes to the next chunk of 2048 samples. So it's yeah, nothing. This is the simplest version where we do the FFT and then do nothing. So here's a brick wall filter, and PV brick wall will 0 bins, and what that means is it's and here's a cute plot trick. You can press E to turn edit mode on. And so what it does then is based on the wipe parameter, it's going to just take a certain number of bins and just set them all to 0. So 0 amplitude, 0 phase, depending on what the wipe parameter is. You might also, there's no undo. There's no undo. You can't Command Z. So we'd have to plot it again or something, which I don't feel like doing. So wipe can be between -1 and +1. If it's 0, there's no effect. So this will also have just be a normal, regular, but that's okay. Sound. We can make it sound different by nothing different. But if wipe is greater than 0, then it acts like a high pass filter, clearing bins from the bottom up. So let's do that. So I'm going to set it equal to 0 initially, and then just do some set commands. But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable so we can more easily keep the processed and unprocessed. So that's a brick wall filter. One of the most basic ways to delay a signal in SuperCollider is using a UGen called delay L. And so once we get up to like, you know, a tenth of the way through the FFT spectrum, we've cut out a lot of the important information. It's a lot of the important information is gone, right? So all we have is like the you know, it's the bins are linearly spaced. So with human voice, a lot of the most prominent information is going to be the fundamental and like the first, I don't know, 50 or so partials. So let's do it again, but we'll go the other way. But that's okay. We can make it sound different by, oops. Okay, I think it's working. We should hear the fundamental come in. There it is. A boo boo boo, a boo boo boo.
The delay of signal is SuperCollider. It's using a
UGen called
delay the CMA of 3 UGens, which includes delay N.
So we've got this kind of underwater effect.
But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable.
Yeah, so like somewhere around here, somewhere around like -0.8, it's like what like Zoom audio sounds like when you have original sound off, because Zoom will just like cut everything like, you know, 8K and above to condense the bandwidth of the signal. I don't know if it's actually doing an FFT, but that's how like, you know, audio compression works on video platforms. It's just like, you know what, we're not going to process this part of the spectrum because it's not essential to understand what people are saying. So they're cutting corners everywhere. So yeah, like something like this. But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. You might, that flavor of the sound might be familiar to you. Okay, but this, I think this is not a particularly intuitive way of specifying sound in like a musical way, because, you know, what we want is to treat this like an actual filter where we can say cut off at 500 hertz, you know, cut off at like high pass filter cut off at 500, low pass filter cut off at 2000, whatever. And this bipolar normalized value is, you know, it's annoying to have to do the math, but we can build that into the synthdiff so that we can be more, you know, just to specify, make it more a more intuitive experience to deal with it. And what I'm going to do here is two PV brick walls back to back. So what we have here is one brick wall filter, which processes the FFT data, and we provide a value called LPF, which is initially 20,000. And we think of this value as a cutoff frequency for a low-pass filter. Easy. But then we just need to map it onto the correct value. So if it's 20, the lowest allowed value, that's going to map to -1. Now, realistically, that is going to filter out everything below 20 hertz as well as above. So, but it's, you know, I'm being a little loosey-goosey with the numbers here, but it's fine. So a value of 20 means the wipe value is going to be -1, which means the lowest possible cutoff frequency. And if it's 0, that means no effect. And somewhere in between, it's going to be, you know, at the appropriate corresponding point. And it's really important to use lin here, because the bins are linearly spaced. We're very used to doing stuff like lin-exp to map from, or explin, just thinking of like, you know, going from like MIDI note numbers to frequency or something like that. But lin is the correct choice here. And then similarly, we then pass that FFT data through another brick wall in series, and we have a high pass filter, initially 20, so passing everything. 20 maps to 0, and 20,000 maps to 1. So now, I'm gonna copy this, and we're not even gonna, there's no wipe value anymore, so we're just gonna do this. But that's okay. We can make it sound different by now we can do stuff like this. I'll do an LPF first. But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable so we can more easily keep the processed and unprocessed signal. Right. And now let's do a high pass filter as well. So we'll set this back to 20,000, which includes delay N and also delay C. But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a
fairly standard and fun thing to do.
So now we have a band pass filter. It only goes from 400 to 2000.
The processed and unprocessed signals separate. One of the most basic ways to delay a signal in SuperCollider.
We can just get a single. Probably can barely hear that. Let's do something where there's actual content. We can get a single bin. Everything else is zeroed. I guess I can do this too. Right. So that's just the bin corresponding to, 250 hertz. We can make a little narrow band. And so you can get kind of like a little, old-timey radio effect if you tweak these values. Maybe something like, I don't know, this.
Add a delay, because that's a fairly standard and fun thing to do.
Yeah, I would call this like the cardboard radio effect, like a little DIY radio, and I don't know, something like that. So that's the brick wall filter. You can, it's pretty easy to make a brick wall high pass, low pass in series, so effectively you've got yourself a band pass. And I think I have another example here, which I'm just going to paste in, where you can create multiple instances of this synth. So I'm using collect, just make 4 of them. And then I'm setting each one of those to have a different band. And this is actually more interesting, I think, if we look at the frequency scope as we do this. So we'll make the synths first. But that's okay. We can make it sound different by full
adding
spectrum.
an effect. Let's add a delay, because that's a fairly standard and fun thing to do.
Let's get, I want this.
Let's declare a second variable so we can more easily keep the process.
So I've made four bands here, 100 to 150, that's this one here. 400 to 750, that's this one here, etc., etc. And so you can see it's a brick wall filter. There is nothing in the empty space between the bands. Okay, let's look at another one. Let's skip around a little bit. Let's do something a little bit weirder. There's a unit generator called PV bin scramble, which I think is kind of self-explanatory. Just reading it. So again, it's same deal. We pick an FFT size. We have some live signal. We take an FFT. We send it through a bin scramble. So this is the FFT buffer to process. A wipe value, a width value, and a trigger. We go back to the time domain, and then we send it out. Pretty easy. So let's look at bin scramble. So wipe scrambles more bins as wipe goes from 0 to 1. And by scramble, it means like swap the location randomly with another bin. So 0 means no bins get scrambled. 1 means every bin gets a new location. So on this thing, it's like it's going to pick one of these bins, take the amplitude and phase data, and swap it with another bin. So 2 bins get swapped. Pretty straightforward. Width is a value from 0 to 1, indicating the maximum randomized distance. So if it's 0, even if wipe is 1, if width is 0, the bins are not allowed to move anywhere. If it's 1, those bins could jump all the way across the FFT buffer, from the first bin to the last bin. And if it's 0.5, that means they can jump no more than half the distance of the FFT buffer. And so 0.1 is a tenth, and et cetera, et cetera. So we're going to do, and then trig is just this is a trigger, a trig control. So when I set this to 1, this trig argument goes to 1 and then snaps back to 0. So it's a convenient way of, we've talked about this before, but it's a special type of argument that allows you to trigger things by just setting them to 1, and they automatically go back to 0. All right, so without any changes, wipe and width are 0 by default, so it's going to be, but that's okay. The regular sound, and then I'll start by I'll make the width 1, and I'll make the wipe. We'll just randomize like a few bins, right? Just 1/100th of the bins. 1 out of every 100 bin is going to get moved to a new random location. But that's okay. We can make it sound different. So I don't hear anything different, but let's do it again. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable so we can more easily keep the processed and unprocessed signals separate. One of the most basic ways to delay a signal in SuperCollider is using a UGen. So in this case, you might hear like a really high frequency beep, 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 beep. That's some low bin that had a lot of energy that got bumped up to like, you know, the 200th harmonic or something. But that's okay. We can make it sound different by adding an effect. Let's add a delay because that's a fairly standard and fun thing to do, especially with voice. So first let's declare a second variable. So now half the bins are fully random. Processed and unprocessed signals separate. One of the most basic ways to Alright, so that's usually going to sound pretty shrieky because with a width of 1, there's a very real chance that lots of bins will get shoved up into the upper stratosphere, and so you have lots of energy at high harmonics. So it's a good reason to like restrict the amount of randomness so that no bin can go too far from its home. So let's do it again. But that's okay. We can make it sound different by adding an effect. Let's add a delay. So this is almost normal. Fairly standard and fun thing to do, especially with voice. But now the bins can move around a little bit. Second variable, so we can more easily keep the processed and unprocessed signals separate. One of the most basic ways to delay a signal in SuperCollider is using a UGen called delay L. It's actually part of a family of 3 UGens, which includes delay N and also delay C. But that's okay, we can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first let's declare a second variable. Oh, pretty cool, right? I mean, I think that's fun. If you tweak it just right, you can get a weird effect that still sounds like me talking, but it's also very wrong. So that's fun. All right, so there's more. I had some other examples. I had one looking at PV mag above and mag below. These will basically pass bins which are whose amplitude is above or below, respectively, a certain threshold. So you can only take the loudest bins or the quietest bins. So that can be kind of an interesting effect as well. The real juicy stuff, and I know I'm over time, and if you gotta go, you gotta go. Maybe you can rewatch this, but I think this is this is like what I've been trying to build to. In the PV chain UGen, there are 3 methods: PV Calc, PV Calc2, and PV Collect. And these are what I like to call the choose your own adventure FFT processing. They basically, you just pass in the magnitudes and phases, and you get to decide exactly what happens to those pieces of information rather than relying on some pre-built PV this, PV that, whatever. So PV Calc, you pass in, you have a function where you pass in 2 arguments called whatever you want, and they represent the array of magnitudes and the array of phases. And then you output an array. So this example, they just reverse both of them. You just swap the order. Let's do an example. PV Calc 2 is a way of combining the magnitudes and phases from 2 different signals. That's how you get your sort of FFT vocoder effect. And then PV Collect, you get to process each bin individually. And you can pass in the index as well. It's a lot like collect, where you operate on a collection, you pass in a thing, and you do a thing to each item. The downside of these is that they can be relatively CPU heavy. So morph, we could try to do a morph. In fact, let me skip right ahead to PV Calc 2. Let me copy that. Yeah, so a spectral morph, basically taking aspects of 2 spectra and blending them together. So I have a synth called PV Calc 2. And I am making 2 signals here. One is the same signal we've been working with, that looping buffer. The other one is a sum of 1, 2, 3, 4, 5, 6, 7 sawtooth waves. I'm trying to make a nice little chord here. So just MIDI notes converted to CPS. And I also have a value in semitones that I can use to transpose this whole chord. So let me first start by just playing these 2 sound sources. Well, you know what the first one sounds like, but that's okay. We can blah, 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 blah. So let's just listen to sig 2. I'm going to be extra safe here and set that to be 0.5 because sawtooths are kind of loud. And that sounds like this. Yeah, gradually shift from one to the other. I think that is possible. we can try to do it. So let me just make this 2 channels just so it doesn't sound so bad. So this is the signal we're working with for the second source. And I'm intentionally choosing a rich spectrum thing here. And by the way, Dimitri, if we can't do a satisfying morph, I will do it after the stream ends, and I'll add those files to the live stream code archive. Okay, so here's what's happening here. We take 2 FFTs, one of the first signal, one of the second signal. So 2 local buffs, right? These are different local buffers. Same size. I changed the size down to 1024 because I thought that sounded a little bit better. And then we do a PV Calc 2 on one of the FFTs. So we apply PV Calc 2 to the first one. We pass in the second one. So we have the second FFT chain, the number of frames to process, 2048, and we declare 4 arguments: the magnitudes and phases of the first signal and the magnitudes and phases of the second signal. And we can return just one or the other. So this, let's turn this down a little bit, will just be the first signal. See, oh, and this, get ready to see this a lot because these are big synth defs because there's stuff happening for every single bin. So there's actually like, you'll see the number of UGens when I play this single synth jump up to like the thousands or something. Maybe not thousands, we'll see. Oh, I still have this here. That's not right. I meant to do this. Change the output back to sig. But that's okay. We can make it sound different. Or we could listen to only the second signal. So that's sounds like this. Right, and we can transpose it. So here is, I think, I kind of stumbled on this, and I was a little surprised to find that a Daft Punk-esque vocoder is kind of this simple. So we're using the amplitudes from my voice, but the phases from this summed sawtooth chord. But that's okay. We can make it sound different by adding an effect. Let's add a delay, because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable so we can more easily keep the processed and unprocessed signals separate. One of the most basic ways to delay a signal in SuperCollider is using a UGen called delay L. It's actually part of a family of 3 UGens, which includes delay N and also delay C. I think that's great. That was a lot of fun. Good stuff. Here is what the opposite sounds like. This is going to sound a lot more like a sawtooth wave, and you're going to get like a very slight sense of me talking. Before we play it, so like this example here, we have the sawtooth wave, right? And then we do an FFT of that sawtooth wave, and you know, it's the phases are all pretty regular, right? They're not sort of random as they are in like a speech or some random waveform. And then we're just basically using the amplitudes as a bunch of bandpass filters, right? So the sawtooth magnitudes are kind of very uniform, but we're taking my voice, and you remember that first graph we had with like the little peak at 5 hertz and the 10 hertz and then 25, 26, 27, not hertz, 5th harmonic, 10th harmonic, 26th harmonic. We're putting that profile on the amplitudes of the sawtooth wave, and so that's why we get what we get. It's pretty cool, right? But that's okay. We can make it sound different. And then let's do this instead. I'm gonna turn this down a little bit. It sounds like this, but that's okay. That's not right. I think it didn't finish building the synth down. Yeah, not so good. So the general approach I would try for morphing, to answer Dimitri's question, is something like, I have to think about this. It would be like mag equals, oh, is this gonna work? So this would be, oh, I think this has to be KR, because I think this is control data. or it's not an audio signal. I'm a little scared to use Xfade too. I think this will work. But in preparing this lecture, I definitely crashed the server a couple times and also blew something up once or twice. So I think it would be something that looks like this. Like, no, we can't scale the phases like that. We'd have to rotate them because they're like radians. I'm gonna leave the phases alone, and we'll just use the. It's a lot of things you can do. There's a lot of directions you can take this in, and let's try it this way. Let's say blend.kr 0.3, and this is gonna be 1 minus blend.kr 0.3. So when blend is 0.3, we're going to take 30% of me talking and 70% of the sawtooth. That's got to be mag 2. And then we're going to say mag here. So we're just saying mag is going to be 30% sound 1 and 70% the magnitudes of I'm just triple checking here. Let's try it. All right, if you're wearing headphones, take them off. Take them off. Or mute your volume. Fair warning. I'm gonna take mine off too a little bit and get the meters going. I'm a very irresponsible coder.
But that's okay. We can
okay, it's fine.
Sound different by adding an effect. Let's add a delay because.
I think yeah. So with voice, the phases are generally kind of random. So I think I meant to do phase 2 here. So let's try this. This ought to sound a little better.
But that's okay. We can.
I think I'm running it before it takes this. SynthDef is huge. Like it's like wow. You're sure you want all this stuff here?
But that's okay. We can make it sound different by.
Okay. Yeah. Look at the number of UGens. 3,660. It doesn't look like it's that many. It looks like it's like 12 or something. But there's so many because PV Calc 2 is operating on every single bin of 2 FFT chains. Okay, so now let's try changing the blend value.
But that's okay. We can make it sound different by adding an effect. Let's add a delay because that's a fairly standard and fun thing to do, especially with voice. So first, let's declare a second variable so we can more easily keep the processed and unprocessed signals separate. One of the most basic ways to delay a signal in SuperCollider is using a UGen called delay L. It's actually part of a family of 3 UGens.
I hope that's what you were imagining, Dimitri. There's obviously lots of tweaks to be made, but if you want to think like vocoder style, then you have one carrier, which is the ultimate sound you're going to hear, and this is like the modulator, and the amplitudes, the sort of magnitude profile of this one gets applied to the other one, and then by inserting an expression like this, you can choose how much of each one you want to use. So we're just kind of scaling each one and summing them together. There's probably some clever phase thing you can do. This is what I meant at the beginning when I said like the down and dirty details and like sort of phase wrapping and unwrapping and rotating and like interpolating between 2 phases. It's probably not that complicated, but I just don't want to tinker around with it and like blow something up here. So I had a couple other examples. Maybe I'll just paste them in and put some comments as I upload this because I'm already kind of way over time. I had a feeling this might happen. But those of you who are sticking around for the whole thing, I hope this was really cool. FFTs, oh man, they are great. They are just super great. You can do so much fun stuff. You just get such precise control over the individual harmonics of just any sound, and you have it all in real time. The downside, of course, is that this does get pretty expensive. I had my activity monitor up last night, and every now and then it would just like 99%. I'm like, oh, I broke something. Once or twice the server just quit. It was like, nope, I'm out of here. Just once or twice. So be careful. be careful. It's very easy to mess things up when you have programming language style control over everything. But anyway, that's the FFT and SuperCollider. Feel free to please go ahead and tinker around with all these various PV this and PV that. There's quite a lot of them. And those of you who are doing the working on that next homework assignment, this is fair game. You have one source sound, but you can process it in a million billion different kind of ways. All sorts of FFT stuff. Should be a lot of fun. So that's it. That's it for week 8. I hope you enjoyed. I forget. I didn't look at the syllabus for what's next week. I'm going to go look at that syllabus real quick. What is next week? I think it's like OSC and custom controllers. Should have done FFT here. I switched things around. An intermediate look at patterns. That sounds fun. I'm excited. Let's talk about patterns. Let's talk about patterns a little bit more deeply next week. Yeah, Dimitri, thinking of how we take out bins gradually from one while gradually introducing bins from another. Yeah, good question. So I bet there's a PV that does exactly that. I bet you could do it with PV Calc 2, and that would probably look something like mag equals mag at well, I mean, you could probably, this is not going to be a dynamic version, but it would, like 0 to 512 concatenate with mag 2, 513 to 1024. I think. And then, so basically the resulting magnitude array is half of the first half of the first one and the second half. It may not be exactly this. And I bet there's a PV thing that does it. And I'm going to just look at the names and see if one of these makes sense. Clip. Some of these are, a lot of these are extensions. Oh, well, there's a, this one might do it. It's an extension, PV Morph. I bet you could do it with PV Brick Wall, honestly. Because Brick Wall will just 0 bins at a threshold, and then you can have another FFT, like a separate chain, like your second signal going through an FFT, and a separate Brick Wall filter, and you just have some variable which is always at the same point but acting as a high-pass, low-pass filter, and then you simply sum those signals together, like in the time domain afterwards. So at the end, you'd have like sig equals IFFT, and sig2 equals IFFT, and they've both been brick-walled in opposite ways. And then I think you just like add them together. I bet you could add them together in the frequency domain or the time domain. I think brick wall is where I would start. Whoa! Or this. Oh, that's an extension too. Soft wipe. Is there something called PV wipe? But this is an extension, so you could download the SC3 plugins. But this looks like exactly what you wanted. Yeah, if wipe is greater than 0, it begins replacing with bins from input B from the bottom up. So that's probably the cleanest solution if you don't mind working with extensions. Whew. Fun times. All right, so that's going to be it for this week. Thanks for watching, everybody. I hope you enjoyed. I hope you have some fun with FFT stuff. And I'll be back same time next week for an intermediate look at patterns. So, see you then. Take care. Have fun. Later.